Last time we saw how we can use NPN transistors as overvoltage protection. This time we'll see overvoltage protection using PNP transistors. So let's start. First, we need to understand what is the overvoltage and how we can protect our system from it. If you know this or already have seen this in the previous video, then please just skip to this timestamp. The overvoltage protection shuts down the supply or clamps the output voltage when the input voltage rises above maximum permissible voltage value. An overvoltage condition might occur in the power supply due to faults inside the supply or from the external causes such as surge in the power supply lines. In this protection, we have to set a threshold voltage above which the control circuit shuts down the supply or diverts the extra voltage to other parts of the circuit. And we can use BJTs to protect any circuit from overvoltage. This is the most important applications where BJTs are widely used. Let's take an example where we have some loads like CCR with LEDs or an embedded system. Every IC or power supply has some input voltage range in which it works without damaging. We'll consider CCR for now. We know NPN transistors can be used very easily for overvoltage protection. Please click on this card to watch that video. But we have to use NPN transistors at the returning path of the circuit, that is, on the low side of the load. We call them the low side switch. But in this circuit, we have to keep ground connected and keep the switch in the supply side. The reason is that even when the transistor is fully on, there is still a small voltage drop across it. That voltage drop means the ground is not exactly at 0 volts for that device. For something simple like LEDs, it doesn't make much difference which switch we use. However, an active device like a microcontroller needs its ground to be ground. So when we have a load that requires ground, we need to use a high side switch. The PNP transistors can be used as high side switches for overvoltage protection. Let's consider this CCR as a load box. We'll connect a PNP BJT in series with the load and supply so that it cuts off the supply when the voltage exceeds. Basically, it will act like a switch. We'll name this transistor as Q2. We'll connect one resistor R2 from ground to the base of the BJT. This resistor will pull down the base of the BJT to the ground so that it stays on all the time and current flows to the circuit whenever supply is given. Now when the voltage exceeds, this transistor has to shut down. So to turn this transistor off, we need to add one more BJT which will be connected like this in the circuit. So that when it turns on, it will pull the base of the Q2 to logic level high. That is, to the supply to turn it off. We'll name this transistor as Q1. Now Q1 is a smart device. It should know when to turn on and when to keep itself off. So the base of this transistor should be controlled such a way that up to certain value it will be off, but when the threshold voltage reaches, it should turn on. To do so, we'll use a Zener diode. So when the voltage reaches up to certain value, that Zener diode will go into Zener breakdown and current will flow through it. So we'll connect the Zener diode to the base of the transistor and we'll connect a current limiting resistor R1 so that when input voltage reaches Zener voltage, the circuit shouldn't short. And also it will make sure the base of the BJT Q1 is protected from high input current. Up to normal operation, this R1 will make sure that the BJT is off, but when the input voltage reaches overvoltage threshold, the Zener diode will conduct and Q1 turns on. This Q1 starts conducting and input voltage gets connected to the base of the Q2, and this Q2 will cut off the current in the circuit. Resistor R2 makes sure that there is no short circuit when Q1 starts conducting. Let's take an example that the input voltage is 13 volts and we are designing the circuit such a way that when the voltage goes beyond 18 volts, the overvoltage will get activated and the circuit will be cut off by the transistor. Main requirement of the circuit is that the current handling capacity of the Q2 should be higher than the current flowing through the circuit. Now we'll simulate this circuit. The circuit is the same which we have discussed earlier. Both transistor Q1, Q2, resistors and Zener diode are connected as per our design. And we have connected a CCR using LM317 as a load. And around 0.5 ampere current should flow through this circuit. If you want to know more about the constant current regulators, please check out this video. This diode D3 is a Schottky diode, which is acting as a Baker clamp. In easy words, it helps to improve switching time of Q2 under 100 nanoseconds. Now, if you see the simulation, the input voltage is rising from 12 volts to 20 volts step by step. 0.5 ampere current flows to the circuit without any disturbance up to around 18.6 volts. And after that, Q2 cuts off the circuit. The Zener diode starts conducting at 18 volts and the remaining 0.6 volts is required to turn on this BJT. Well, in the simulation. But in actual circuit, this will change a very little bit, and this configuration makes sure that our circuit is well protected from overvoltage. Well, that's how a PNP transistor based overvoltage protection works. So far we have seen all the core applications of BJT. Well, there are many more applications where we can use BJTs, but that's it for now. Next time we'll learn something new. Till then, stay tuned. I hope you got something from this. If you haven't, you can watch the video again. Still, if you don't, you can ask your doubts in the comment box below. Hit the like button if you like this video, subscribe to my channel, and finally, thanks for watching.